Alright, so this is lecture 21 of... Noticed I'm bleeding. It must be because of all the painful integration we were doing last time. Did anybody enjoy the integration we were doing last time? Alright, so we had this nasty mess that we were working on for sums of normal being normal. And we showed by grouping, all we had to do was do it once. If we could prove a sum of two normals is normal, then a finite sum is normal. And we had this horrible completing the square that we had to do. And we had all these constants floating all the way here and there, and did we complete the square correctly, and then what happens when we put this out and do all the integration. What I want to do is I want to go back and I want to revisit this, but much more carelessly, because we don't have to be careful. And this is the beauty of the theory of normalization constants. It's one of my favorite ideas in the subject. So to recap, we have the density of a normal with mean 0, variance sigma squared, 1 over the root 2 pi sigma squared, e to the negative y squared over 2 sigma squared. Let's say x1 and x2 are normal, mean 0, variance sigma I squared. We want to calculate what's going on for x. We believe it's normal. And we know that the expected value of x, the mean, is going to be 0. And we know the variance of x is going to be sigma 1 squared plus sigma 2 squared. The purpose of this is that if we can prove that x is normal, there's only one normal it can be. The normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. So when we're doing the calculation, all we have to do is get close to the answer, and then it will automatically correct to the right normal. Okay? So I'm not going to prove that it is a normal with mean 0, variance sigma 1 squared plus sigma 2 squared. I'm going to prove it's some normal. And once I know it's some normal, I'll know which normal it is. Okay? So we had the density of x. This was the theory of convolutions. Was equal to the integral from minus infinity to infinity of f x1 of t f x2 of x minus t dx. And then let's look at the integrand. I claim the integrand is of the form c e to the negative t squared over 2 sigma 1 squared e to the negative x minus t squared over 2 sigma 2 squared. And if you want, actually, at this stage, we're going to be a little bit better about what c is, but I don't care. Everybody agree the integrand looks something like this? Yes? When I do some algebra, this is the completing the square. I get some constant, e to the negative a t minus b squared, and then e to the negative c x squared. So when I complete the square, I know I have a negative x squared piece coming from this. I'm going to be adding and subtracting. I'm still going to get a negative piece over here. Yes? Oh, sorry, it should be dt, thank you. So when I collect things and I do the squaring, I'm going to get something. And actually, sorry, this should be bx. Because I'm going to have some x over here. I don't know exactly what it is. It's going to look something of this form. Okay? If you're not positive that this term is going to be negative, we'll deal with that in a moment. For now, I'll just assume that it's going to be negative, and I'll show you in a moment it has to be negative. Right? It's going to look something like this. We were spending a lot of time yesterday trying to figure out what the a and the b were, and this was giving us like sums of reciprocals of the sigmas, which wasn't pleasant. Now let's do the integration. All right, so now we have fx of x to be c e to the negative cx squared. This has no t dependence, and then I integrate from minus infinity to infinity of e to the negative a t minus bx squared dt. This is some finite number. I don't care what it is, it's finite. Okay? This is called integrating without integrating. It's something. Okay? So what I get at the next stage is I get fx of x is some new constant. Let's call it c tilde, so that we know that it's related to the constant we had a moment ago. Didn't want to move over. So we have c tilde, And then we have e to the negative c x squared. Okay, it's got to look like that. Here's now a proof that this has to be a negative. This is a probability distribution. If this number was 0 or positive, if I now did the x integral, I'd get plus infinity. So clearly, c is less than 0 as it's a probability density. This has to be a normal distribution. So the variance is, I want to write it as e to the negative x squared over 2 sigma squared. So 1 over 2 sigma squared equals c. Yes?
Sorry, why would, if c is less than 0, then negative c would be positive 3?
Right, and if this is an e to the positive x squared, when I integrate from minus infinity to infinity, that'll be plus infinity.
Minus c would be positive because you have minus c.
Oh, I'm saying C, if I misspoke, I apologize. C is positive. I'm saying there's a negative sign in front of the C. I like to always write my constants positive if possible. So here we have C. Oh, I see, I wrote it the wrong way. Yes. I think I said one thing and wrote the other. We can check the tapes. So C has to be greater than 0, because if C were less than 0, then you have e to the positive x squared. And then that would integrate to plus infinity. So if you actually want to figure it out, you would get C as 1 over 2 sigma squared. But we know if it's a normal, there's only one normal it can be. It has to be the normal with mean 0 and variance sigma 1 squared plus sigma 2 squared. So we know that C has to equal 1 over 2 sigma 1 squared plus sigma 2 squared. And we know big C tilde has to be 1 over square root of 2 pi sigma 1 squared plus sigma 2 squared. You can go through the algebra and do the completing the squares properly. And you can do all the integration properly and say, okay, I've got an exponential, I know how to do the integral of an exponential, I'll do a change of variables. What I'm saying is you don't need to. This is called the theory of normalization constants. The theory of normalization constants. And to me, it is absolutely remarkable. It allows us to evaluate these integrals without going through and doing the painful integration. We don't have to do the painful completing the squares. We just need to know you can complete the square. Okay, so I go through this in excruciating detail in the book. We'll do another example of that later today with ChiSquare. This will allow us to bypass the need of knowing the multidimensional spherical coordinates. How many people remember spherical coordinates? It's kind of hoping the people who had me in Calc 3 would raise their hand, but okay. Now, actually, one of the reasons why it's hard to remember spherical coordinates is the physicists and the mathematicians have different conventions as to where the angles go. But for some of the problems, we would actually need to have, spherical coordinates in 2,000 dimensional space. Most of you, I'm assuming, have not remembered what those are. We can bypass all of those with the theory of normalization constants. Okay. So we're going to shift now to the gamma function. So the gamma function is related to the normal, and it is going to be related to the next distribution we're going to look at today, the chi-square distribution. It's defined as follows. Gamma of s is the integral from 0 to infinity of e to the minus x, x to the s minus 1 dx. And I want the real part of s to be greater than 0. So you are allowed to have s be complex, and for some applications, it is very useful to have s as a complex number. If you look at this, this should look like bad notation by the mathematicians. Yes? Where does the notation look bad? I think I heard everywhere, but it can't be bad everywhere. There's got to be at least something to that. I mean, e to the negative x, that looks nice. That's going to give us lots of decay. Yes?
Is it writing the real part of s?
No, this is just allowing me to eventually teach some of you in complex analysis and say, remember in probability?
S might look like a 5.
I'm sorry? Oh, well, one thing is s does look like a 5, and that is problematic. Yes.
can rewrite x to the s minus 1 as x to the s over x, or you can move it.
Right, so it looks strange. Why would we want to write it as x to the s minus 1? If our parameter is s, why not just call it s over here? The reason is you can write this as e to the negative x, x to the s, and then dx over x. And the reason you want to do this is basically a multiplicative variable. If I rescale x by a factor of 5, dx over x doesn't change. So in terms of the measure of the space we're using, we're not really doing much on measure theory right now. This is the measure you want to be looking at things, and the natural function is x to the s. Now, whenever you have an integral that's improper, what's the first thing you should think about when you get this improper integral? Does it converge? Okay, so there are really two dangerous places in terms of does this converge. The first is what happens as x gets close to 0, and the second is what happens as x goes to infinity. Well, when x is getting very, very close to 0, what does e to the minus x go to? As x goes to 0, e to the minus x goes to 1. And x to the s minus 1 is okay if the real part of s is greater than 0. So for the rest of today, I'm going to just assume s is a real number. I'm not going to worry about real part. I'm going to just say, let's just let s be positive. So I'll say s is greater than 0. And the reason is, this looks like 1. Let's say s is a half. I'll get x to the negative a half. X to the negative half does blow up, but it's integrable. The integral of x to the negative a half is going to be x to the 1/2 over 1/2. Right? So this will be fine. It's not going to be a problem. If I took s to be 1/4, then I would have x to the negative 3/4. And I would have over here 1/4. So as long as the real part of s is greater than 1, the x to the s minus 1 is fine as x goes to 0. If, however, s was equal to negative 1, then I would have x to the negative 2, and that would blow up if I tried to do the integration. So as long as the real part of s is greater than 0, it's fine. The next thing is what happens as we go off to infinity. Well, as we go off to infinity, we just need to make sure that this integrand has enough decay. And so this is where you would use L'Hopital's rule. The exponential decays a lot faster than a polynomial grows. So no matter how finite s is, it's a finite number. This is an only growing polynomial. So one thing you could do is, at infinity, you want to look at the limit as x goes to infinity of x to the s over e to the x. Without loss of generality, we can assume s is an integer. Just take the ceiling, right? Because if we take the ceiling, that only makes the integrand larger, and if that still goes to 0, we'll be fine. So you just need to show that this has enough decay. There's a lot of ways you can do this. One of my favorites is, let me look at it like this. If I can show that x to the s over e to the x halves goes to 0, then when I have my integral, I'll have my integral e to the negative x halves, e to the negative x halves, x to the s minus 1 dx from some big number m to infinity. If this part is bounded, if this part goes to 0, I still have some exponential decay left. So what I'm doing is I'm borrowing a little bit of the decay from the exponential. This is an extremely common technique. And this is, you just need to do stuff like this very rigorously. Real analysis, not surprisingly, is a class where you get some training and stuff like this. But anyway, this is a good way to just see what's going on. If this is bounded, I can borrow a little bit of decay. I don't have to take x over 2. I could take x over 2016. Any little bit would be enough. And now if I wanted to use L'Hopital's rule, if s is an integer, I just take s derivatives up top, and I'll get s factorial times 1. And then I'll just get 1/2 to the s, e to the x halves. So using L'Hopital, we see that this will go to 0. If it goes to 0, it's bounded so that the integral will converge. So the whole point of all this is at least a well-defined function. Okay? So any questions about this? We're getting to see some really good analytic techniques today. Okay. Any baseball fans? All right, so I will be doing my baseball lecture on Friday. For those of you who have had me before, it'll be a very small update in honor of the World Series. So that's going to be a lecture that will be a series of applications of probability. So this will give you some time to just digest all the material that's coming in. So the Friday lecture will be a lecture on applications. There is, I think, a bunch of perspectives who are visiting on Friday. I've been told that perspectives are visiting on Friday. So if anybody is hosting anybody, it will be an accessible lecture. You really only need multivariable calculus for this, but all you need for multivariable calculus is if you can integrate once, you can integrate twice. So if anybody does have anybody, you're welcome to bring them to that. All right. We've defined the gamma function. We should now calculate some of its values. Anybody want to give me a good value to check for S? If you had to choose any value, and I'm making you choose one right now, 1. All right, so gamma of 1 is the integral from 0 to infinity of e to the minus x dx. This becomes e to the minus x, and the minus sign causes me to flip the order of integrations. We get 1. Not so bad. Another value. 2. Okay.
Why isn't it negative e?
I'm sorry?
Why isn't it negative?
It is, but I flipped the order of I flipped the value at the where I evaluate it, so that I incorporated the minus sign there. So if I take 2, I'll get gamma of 2 is the integral from 0 to infinity of now be x e to the minus x dx. How should we do this? Yes?
Integration by parts?
Integration by parts. You are not allowed to hate integration by parts, or if you hate it, you have to keep it to yourself. This is a big tool for integrating in this class. So we'll take u equals x, we'll take dv equals e to the minus x dx. This is a good way to do it because now when we integrate by parts, we're going to decrease the power of x. And we'll get du equals dx, we'll get v is negative e to the minus x. And so then we get gamma of 2. This will be uv at 0 infinity minus the integral from 0 to infinity of v du. When I look at the boundary term, we have x times e to the minus x at 0 and infinity. What is the boundary term at 0 and infinity? So what's our boundary term at 0 and infinity? So 0 times e to the negative 0 is 0. And if I have an infinity times e to the negative infinity, all right, that one's a little bit more work. You know, infinity times e to the minus infinity. But that's exactly what we've been doing multiple times with local power. You know, polynomials grow significantly slower than exponentials. So the boundary terms vanish. So this piece we don't have to worry about. The negative reinforces with a negative, and we get that this is the integral from 0 to infinity of e to the minus x dx. Oh, that looks very familiar. It's equal to 1. So gamma of 1 is 1, gamma of 2 is 1, so by induction gamma of 3 is 1, right? No. If you go through and do the algebra, you get gamma of 3 will have an x squared. So how many times do you think you'll have to integrate by parts? Twice. So we're going to just fast forward a few moments. We did the integration by twice, and when the dust settled, we got 2. Oh, it's the Fibonacci numbers, 1, 1, 2. Right? So gamma of 4 should be 3. All right, let's test that conjecture. How many times will we have to integrate by parts? 3 times. So we will fast forward. I've done the integration by parts for you 3 times. And we get 6. 1, 1, 2, 6. All right, anybody want to guess the next? 24. All right, since you're saying 24, I'm assuming you want to say it a different way.
5 minus 1 factorial.
Oh, even better. 5 minus 1 factorial or 4 factorial. And this would be 3 factorial or 4 minus 1 factorial. This would be 2 factorial or 3 minus 1 factorial. This is then 1 factorial, and that's 0 factorial. And so this leads us to the following conjecture. Gamma of n plus 1 is n factorial if n is a non-negative integer. Plus 0. So we're going to prove that, and that will give us some idea of why we care so much about this gamma function. It's related to the factorials, and in fact it becomes a nice way to continuously interpolate the factorials. Now you might ask, why do you want to continuously interpolate the factorials? What does 4 factorial mean to you? Yes?
Number of ways to order 4 single.
Number of ways to order 4 people when order matters. What would 4.5 factorial mean? We only have 4 people in the front row right now. If somebody from like the second row wants to push like some of their feet or whatnot into the first, we can't put half of a person into the first row. You're fine. You're only getting into the second row. We can't talk about ordering 4.5 people. Okay? So when you're thinking about what the gamma function means, it has a nice interpretation when the arguments are integers. When the arguments are not integers, we lose that interpretation. But that doesn't mean we can't talk about these values. And so when we put in integer arguments, it does collapse to something with combinatorial significance. The other thing is, I'm not sure how much of this we're going to do this semester. Now that we have a way of writing these factorials as integrals, we actually have the possibility of using techniques either from real analysis or complex analysis to estimate n factorial, to understand it. We now have the tools of calculus at our disposal. You can't take derivatives of discrete valued items. If your inputs are integers and your outputs are integers, I can't take a derivative. I can't take the limit as 5 goes to 4. 5 doesn't go to 4. I need to have some kind of continuous variable to be able to apply calculus. And that's the whole point of what we're doing here, is we are going to have a continuous variable now. So let's look at gamma of s plus 1. This is going to be the integral from 0 to infinity of e to the negative x to the s plus 1 minus 1 dx. Let's integrate by parts. U is x to the s plus 1 minus 1. dv is e to the minus x dx. What's nice is I really don't have to prepare today's lecture. I really don't have that much choice in what I'm doing. Right? I just have to quickly look and say, okay, I'm talking about the gamma function. Boom, 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 boom. It is all natural now in terms of what to do. I want to have u to be this because I want, when I'm integrating by parts, I want to decrease the power of u. I want to get down to just a lone exponential. So then du, well, s plus 1 minus 1 is just s, so I would get s x to the s minus 1. And then I would get v would be minus e to the minus s. Do I have to worry about the uv term? No. The uv term vanishes as before, and we get gamma of s plus 1. The negative sign is reinforced, and we'll get the integral from 0 to infinity of e to the negative x to the s minus 1 dx. I'm going to pull outside the s. But what is this integral over here? Gamma. So we get gamma of s plus 1 is s gamma of s. So the way you should view this is, if you know the value of gamma at s, you know the value of gamma 1 unit beyond that. So we really only need to understand, say, 0 less than equal to s less than 1. If we know what's going on in that strip, if I now want to know what's going on at s equals 3.5, well, if I want to say s at 3.5, I just need to know what's going on at 2.5. If I want to know what's going on at 2.5, I just need to know what's going on at 1.5. If I want to know what's going on at 1.5, I just need to know what's going on at 0.5. So if we can understand gamma in any strip of length 1, we understand gamma everywhere. Okay? So then we would have to try to understand what's going on for the gamma function in one of these intervals. And if we can then translate that anywhere we want. All right, so a couple of things to note. The first is, this is called the functional equation of the gamma function. Functional equations are extremely useful. It allows us to reduce the analysis, as I said, to one interval, and then we can deduce what's going on in others immediately. What else can we say about this? It's an extension of the factorial function. So your gamma of n plus 1, if you do a little work, is n factorial and non-negative integer. If I wanted to know what negative 1/2 factorial equals, what value would I want to take for n? Let's see, let me try this right. What do I want to take for n? Well, if I take n equals 1/2, I would then get 1/2 factorial. I don't want 1/2. What do I want? Not 1/2, negative 1/2. So gamma of 1/2 is negative 1/2 factorial. So negative 1/2 factorial. Do not ask me what that means. It's the integral from 0 to infinity of e to the negative x, x to the, plugging in here, oh, sorry, I'm putting in 1/2. Wait a minute. I'm putting in n equals negative 1/2, so I just want to do things like gamma 1/2. So this would become negative 1/2. So I want to evaluate that integral. Okay? If I can evaluate that integral, I now know what negative 1/2 factorial is. Does anybody have any idea combinatorially what negative 1/2 factorial means? Okay. You've all seen it. Not only have you seen it, you've seen it today. Anybody know where you've seen it? Yes.
Is it like the square root of 2 pi in the denominator?
It's extremely close to the square root of 2 pi, yes. And the normalization of the normal. So I will explain where that comes from. So I just want to say one last thing about extensions. We've actually seen something like this early in the semester. So if I look at this expression, 1 plus x squared plus dot dot dot, this is equal to 1 over 1 minus x, at least if the absolute value of x is less than 1. So you have this series which agrees with this nice closed form function if the absolute value of x is sufficiently small. But this thing on the right-hand side makes sense for more values. You should think of the gamma function like that. It agrees with the factorial function at the integers. So there's a lot of different ways of evaluating what this integral is. This is an extremely important integral. I go through in great detail in the book, and I think the appendice is giving multiple ways. Some of them use tangent identities and whatnot. If you enjoy integration, I strongly encourage you to read those pages, or skim those pages and just get a sense of how you would calculate that. What I want to do now is I want to try to give you a sense of why you might care about these quantities. Okay? You always want to be able to answer the who gives a damn, right? There's a lot of material we could do in probability. Why am I choosing to spend so much time on the gamma function? Right? Do I have to motivate the importance of the normal distribution? We can all agree that the normal distribution is important. Okay, let's calculate the, let's say x is normal with mean 0 and variance 1. And I want to calculate the 2mth moment. I'm not going to bother calculating the odd moments because the odd moments will just be 0. This is the integral from minus infinity to infinity, 1 over square root of 2 pi, x to the 2m, e to the negative x squared over 2 dx. Let's see if I can do this well. The first thing I claim is that this is the same as twice over square root of 2 pi, the integral from 0 to infinity of x to the 2m e to the negative x squared over 2 dx. Then rather than going from minus infinity to infinity, oh, yes, I can just go from 0 to infinity and double because it's even. This is why I don't want to deal with the odds, because I wouldn't be able to do this trick. Everybody happy with this stuff? How many of you enjoy having an integral involving e to the negative x squared? What would you rather have as the argument of the exponential? What function is much easier to integrate? Yeah, so let's just get rid of the 2's, then 2's cancel. Okay, no, we can't do that. Somebody tried to do that on an exam once, and they thought that if they just wrote down the right answer, I wouldn't notice the wrong algebra along the way. You can't just cancel the 2's. Right? But what you can do is you can introduce a new variable. Let's let u be x squared over 2. Okay? Then if that's the case, then x squared is equal to 2u. Now du would be equal to take the derivative, I'll get x dx. So that means dx is equal to u divided by x. X is equal to the square root of 2u. So du would be 2u to the negative 1/2 du. Have I done the algebra correctly? Because dx is du over x, x is the square root of 2u. Everybody comfortable with the algebra? Okay. So let's see what we get now when we do this change of variable. So now, one last thing is, as you know, I like to be extremely explicit. X is going from 0 to infinity. What's the range for u? U goes from So if x goes from 0 to infinity and u is x squared over 2, what's the range of u? 0 to infinity. You've got to be a little bit careful with your change of variables. Imagine x went from minus infinity to infinity and you did this change of variables. What would you get for your range of u? Well, when x is negative infinity, u is infinity, and when x is positive infinity, u is infinity. This is one of the most common mistakes people make when they're doing these change of variables. Is you've got to make sure that if you're doing these change of variables, you don't cover the region twice. You want these strictly, these monotone increasing, monotone decreasing change of variables. And so if I try something like this from minus infinity to infinity, it's going to lead to an error. Now, this is like a siren, glaring, blasting, whatever word you want to use, if you somehow get your integration goes from infinity to infinity. That should tell you you've probably done something wrong. But just be aware that this is a common mistake. Okay, so now we're calculating the expected value, and this is going to equal, we have 2 over square root of 2 pi, integral from 0 to infinity. X to the 2m is now the same as 2u to the m. So it'll be 2 to the m, u to the m, right? And now we have e to the negative x squared over 2. Well, that's going to be e to the negative u. And then dx is going to become 2 to the minus 1/2 u to the minus 1/2 du. All right, we've got a 2 to the minus 1/2, a 2 to the minus 1/2 down here, and a 2 up there. They all cancel. So we get a 1 over square root of pi. We have a 2 to the m. We have an integral from 0 to infinity of e to the minus u. And then we have a u to the m minus 1/2 du. What does this look like? It looks like the gamma function. It's almost the gamma function. What should I have? There's one part up here that's annoying. Yes?
The minus 1/2?
Yeah, I don't want a minus 1/2. What do I want?
Minus
1. So I just cover up the 2? No. How do I get that fixed? What do I do?
add 1 and subtract 1 to the exponent?
I'm sorry, add.
1 and subtract 1 to the exponent, so add 0.
Okay, I would have added a half and subtracted a half. It doesn't really matter how you do the grouping, but yes. So this is now the same as 2 to the m over square root of pi, integral from 0 to infinity of e to the minus u to the m plus a half minus 1 du. What is this integral? That's just gamma of m plus 1 half. So this is 2 to the m gamma of m plus a half divided by square root of pi. Okay? So hopefully this gives you some idea of why we care so much about the gamma function. The gamma function is a great way to get the moments of the normal distribution. This is the nth moment. It's having trouble following today. What's the easiest value of m to look at? What value of m would you like to look at?
Half 1.
I'm sorry?
Half?
Not 1/2.
Negative half.
Not negative a half. 0. Why 0?
Well, 2m simplifies to 1.
I'm sorry?
The 2 to the m simplifies
So
to 1.
the 2 to the m simplifies to 1, but 2 to the m is not really what's bothering me. What did we just calculate? We just calculated the 2mth moment. Which is the one moment you know before you start? I'm sorry? Not the first. The 0th. What's the 0th moment of any probability distribution? 1. So this is a great way to check and see if our normalizations are correct. The 0th moment should be 1. 0th moment is 1. So if we take m equals 0, that's going to give us 1 is equal to gamma of a half divided by square root of pi. And you'll then get gamma of 1/2 is square root of pi. So in fact, here is one way to calculate gamma of 1/2. I need to know that this is the correct normalization constant. I have to do the polar trick, but here is a way to get gamma of a half. Now that we know gamma of a half, we know gamma of 3/2, 5/2, 7/2. Okay? So if you now want to calculate the other moments, a really good exercise is show the expected value of x to the 2m is 2m minus 1 double factorial. So there's a lot of great stuff you can do here. I'll put some additional comments on stuff related to this. Okay, so the gamma factor, the gamma function encodes all the moments of the standard normal. That's remarkable. And if we want to know how fast these moments are growing, we would want to know something about how fast factorials are growing. And there's a lot of things you can do. There's a limit to how much time you can spend. But gamma of 1/2 is the most important one, and we're getting now that that's equal to the square root of pi. Okay. Anything else on the gamma function right now? Okay, so we're comfortable with the gamma function. We see at least, here's one reason why we care about it. Alright, so what I want to do now is, I think we have a little bit of time left, I want to talk about a new random variable, chi-squared with new degrees of freedom. So this is a chi-square, new degrees of freedom. We're not going to have time, I think, today to do all that I want with it, so we'll probably continue with this on Monday. Because I want to give you, Friday's class to just kind of relax a little bit, digest all the stuff that's been coming in, and catch up. And then we'll go back to Applied Closed Mathematics on Monday. All right, so I want my density to be the following. And I just want to make sure I write it correctly. It's 1/2 to the nu halves gamma of the nu halves x to the nu halves minus 1 e to the negative x/2 if x is greater than 0 and 0 otherwise. Okay. So this is a chi-squared random variable. So different values of nu give you different choices. I strongly urge you to plot a couple of values of nu and see what it looks like. The question is, of course, why do we care about chi-squared random variables? Okay. Anybody remember from statistics why we care about chi-squared random variables? Yes.
So for like tests of homogeneity and independence, they're
Uh-huh.
really useful to see how like abnormal your result
Yes.
is.
But why are chi-squareds arising?
They're like, where are the normal or something? They're like,
Who likes to square things? Let's square things. Give me a nice variable to square.
Like X.
No. Well, yes, but I want a distribution for x. Normally, when I'm asking for a distribution, I want the
uniform one,
I could do uniform, but I want something else.
normal.
Normal. Right? Let's say x is normal 0, 1. Let's say y is x squared. And we want to calculate what's the density of y. We can use the CDF method. It's a wonderful method. The probability, the cumulative distribution function, this is the probability that big Y is at most little y. One of the reasons I like doing this problem is it has a very natural place to make an error. And so I will hopefully not make the error and just warn you about the possible error. This is the same as the probability that x squared is thus equal to y. This is the same as the probability that x is thus equal to the square root of y. Correct? Okay, I see one person shaking their head. 2 people. 3 people. A lot of people. Okay. The mistake here is that x squared is at most y. X could be positive or negative. So we have to be a little bit more careful and say negative root y less than equal to x less than equal to square root of y. And this is equal to the cumulative distribution function of x evaluated at the square root of y minus the cumulative distribution function of x evaluated at negative square root of y. Now this is a little bit sad at this point because we don't know the antiderivative of the normal. And I need to evaluate the antiderivative of the normal. Fortunately, what am I going to do? I'm going to immediately take the derivative. I really see no point in integrating and then immediately taking the derivative. Right? This is giving us the cumulative distribution. Big Y is at most little y. If I want to find the probability density function, I take the derivative. So I would get little f of y is equal to the derivative. So I'll do it very slowly. Big Fx at square root of y minus big F of x at negative square root of y. And now I have to use the chain rule. So I will get the derivative of big F at square root of y times the derivative of square root of y. The derivative of square root of y would be 1/2 y to the minus 1/2. And for the next piece, when I take the derivative, I will get the minus signs will eventually cancel. I'll get fx prime at negative square root of y 1/2 y to the minus 1/2. I can now combine because the derivative of big F of x is little f of x, and that's the normal density. And because the normal density is even, evaluating at square root of y and y is the same. So the 1/2s will cancel, and I'll get the density of the normal evaluated at square root of y to the minus 1/2. Okay, let's continue doing some algebra. This becomes 1 over square root of 2 pi e to the negative square root of y squared, which is y over 2, y to the minus 1/2. How do you think I want to write y to the minus 1/2? How do you think I'm going to want to write y to the minus 1/2?
Like the
y to the 1/2 minus 1. Because everything we've been doing today, we've been saying we want, if it's the gamma function, we want a minus 1. Well, now let's look at what we have. This is the same as 1 divided by 2 to the 1/2. Now we know the square root of pi is just gamma of 1/2. E to the negative y over 2, y to the 1/2 minus 1. This is a chi-squared random variable with 1 degree of freedom. So the square of a standard normal is a chi-squared with 1 degree of freedom. This is one of the reasons why chi-squared variables come in so many places. Is if you have errors, if the errors are normally distributed and you square them, you will get something that's essentially a chi-squared up to some kind of scaling. Is there a question? Okay. So this is just now using the algorithm to try to give a sense of what's going on here. I've never proved that this is a probability distribution. What are the two things we should check?
That it's non-negative and that it integrates to
Non-negative and integrates to 1. I don't know about you, I'm getting tired of integrating today. It's been a long day. Clearly it's non-negative. I'll leave it as an exercise to you to prove that it integrates to 1. If you think about it, boy, does this look like a gamma distribution, gamma function looking over here, and this is probably chosen so that things are right. It's not exactly a gamma function. Notice the gamma function has an e to the minus x, and a chi-squared variable has an e to the minus x/2. This is why I checked my notes to make sure I didn't do this wrong. Depending on which problem you're doing, different normalizations are slightly better. It is useful to define the chi-squared distribution with an exponential argument of negative x/2. It is convenient to define the gamma function with an exponential argument of minus x. You've got to pay attention to where you are and what you're doing. All right, so this will now give us a nice function. It's going to be a probability distribution, and we have a free parameter. So depending on the different choices you take for new, you get different shapes. So we will be looking a lot about this on Friday's class. It's actually a really good time in the semester to have a lecture to just stop, pause, reflect, see some applications. It's also during the World Series, so it's a really good time to do a baseball lecture. Okay? So a normal distribution, if you square it, if you square standard normal, you get a chi-squared. Now, I'm erasing it right now, but what should you do as soon as I give you a chi-squared distribution? What two questions should you ask? What's the mean? What's the variance? All right, so I'll assume you've done that, and I'll let you go home and figure out what those are. Now let's say we have x1 plus xn, and then xi, we'll say it's a chi-squared distribution with mu I degrees of freedom. And we'll call this sum x. Anybody want to guess what kind of distribution the sum of chi-squared random variables has? What would you guess? I'm sorry? Chi-squared, but that's not enough. So we guess x is chi-squared. You have to tell me how many degrees of freedom. Which chi-squared is it? I'm sorry?
N times vi, or n times n minus 1.
Well, x1 is nu 1, x2 is nu 2, x3 is nu 3. So what do you think it would be? Yes?
It's going to be the largest number of degrees of freedom of all the x and y's.
Not the largest.
That's why.
What do we do for the normal? We summed the variance. So here, a natural guess maybe it's nu 1 plus nu n. The argument is actually a little bit easier if the nu's are integers. It's even easier if they're all ones. We'll do the general case on Monday. How do you think the proof is going to proceed? Yeah, it's going to proceed by grouping. If we can show that the sum of two chi-squareds is a chi-squared where you add the degrees of freedom, then we can just march down and do any finite sum. Okay? So we'll do that, and again, it's going to be very similar to what we did today. This is one of the few days where it would be nice to have, in some sense, an hour 15 class, because then we could do the integrating without integrating for the chi-squareds. If you don't, if you want to do it by brute force, you need to know the n-dimensional spherical coordinates, but you don't want